Hi, my name is Dr. Matthew Michael. I'm a lecturer of mathematics at NGIT in Newark, New Jersey. I'm going through each one of these topics from Boyson de Prima's 10th edition of the textbook. They've created a series of PowerPoints that some of the lecturers can use. I'm using them to try to explain to my students how to think about these problems, how to work through these problems, how to kind of understand their own textbook. So these are their slides, not mine. I'm going to keep trying to work through these. So, we finished Chapter 1, and we're continuing on to Chapter 2. This is typically typically the second section. I tend to go slightly out of order here and do Section 2.2 first. So this is actually going to be this would typically be my second lecture from Chapter 2. But a couple of these early stuff is very useful to understand, like the definition of a linear first-order ordinary differential equation has the general form that the derivative of y, dy dt, is equal to a certain rate function, where that rate function has a linear y term, such as examples seen in the bottom two equations. Y prime is equal to negative ay plus b, or dy dt is equal to p of ty is equal to g of t. Both of these terms are useful in their own respects. The first one, constant coefficients, which can be very useful in money problems or also in mixing problems. And the bottom one is for more complicated situations, which could vary. So the second one is going to be more complicated, but it has a lot of really rich mathematics. Now that first case, I can actually use techniques from 2.2 or from Chapter 1 on separable equations. The idea that the y variable can be integrated using the natural log function. Keeping negative a to that other side, dy over y minus b over a can be integrated. That's the natural log. E both sides, and I get a solution of y is equal to b over a plus k e to the negative. They wrote down positive, but it's negative a t. Now k is some positive constant. We haven't really discussed what that is, but here's what it's kind of saying here. That plus c, which originates from an indefinite integral, well, e, which is a constant, roughly 2.72, raised to some other constant, well, that's going to be itself a constant. So why carry around two constants? Just put them together and merge them into a single constant k. Notice this k value can be positive or negative, depending on the need. But we can also be more complicated with a non-constant case like p of t and g of t. And in this case, we're not going to be able to use the same technique. We're going to have to come up with a more carefully constructed formulation. And this is going to be based on the product rule. So let's take a look at an example of this. Notice in this case, my forcing term on the right-hand side, by forcing I mean non-y term, notice that isn't a constant. So even though the 1/2 in front of y is constant, that 1/2 over 1/2 e to the t over 3 is going to cause some issues. I can't separate them. So what I do is I multiply both sides of the equation by some unknown function mu. Now this mu, because I'm multiplying a derivative and the y function by mu, I can take a look and compare it to the product rule, which is very, at this point should be very well known to you, that the derivative of the function mu and y multiplied together is mu y prime plus mu prime y. And if you look, that first term is identical to the first term we see here. The second term is where it differs, but there's still a y term in both of the second terms. So if I happen to say that this d mu dt, this mu prime, is equal to 1/2 mu, well, I solve for mu, getting that mu is equal to e to the t over 2. And because of this, I can, well, let's check. Let's see if I plug in e to the power t over 2. Well, yeah, that is the product rule, right? Because e t over 2 y prime plus, well, the derivative of e to the t over 2 is 1/2 e to the t over 2. The only cost I have to pay to using this is I have to multiply this exponential by this exponential. That's not 2y. That becomes e to the 5t over 6. So merging these two together into a single derivative, I actually get rid of this y prime term. Because when integrating, this y term, which is unknown and unsolvable at the moment, well, unsolvable here, suddenly becomes much more attainable. And exponential functions are very easy to integrate. So let's solve for y by dividing by this exponential. Notice we get the t over 3 term again right here, but now we get the negative, or the inverse of mu. So we get a general solution of 3 over 5 e to the t over 3 plus c e to the negative t over 2. And depending on which initial condition we're interested in, it'll be one of these different colors or yet another different path we might take. Notice they all kind of converge along this belt of functions. Notice we can actually get a formula for this technique in this general form where the coefficient of y is a constant and the forcing term is variable. Using this technique, we get that mu is equal to e to the at. And so that my formulation of this will work every single time. After all, that's effectively what we did here. Let's try it again. Notice I have a forcing term, 4 minus t, and I have an a, which is negative 2. So plug that in to our formulation. I get e to the y is equal to e to the positive 2t times the integral e to the negative 2t times 4 minus t dt, plus a constant e to the positive 2t. A little integration by parts among friends, and I end up getting a solution when fully simplified of y is equal to negative 7/4 plus 1/2 t plus c e to the positive 2t. And you can see all the different paths you might take. Note that we don't have to say that the coefficient of y is constant. We could just say that it's continuous. And then, well, that mu prime becomes p of t mu. In that case, the formulation for mu is a little bit more complicated. And that k term, which some of you might have noticed should have been there to begin with, that k term actually isn't imperative. That's why we're saying k is equal to 0. It's not really adding anything. Well, technically, I guess it kind of is adding anything, but you know what I mean. It's not adding any information. If we did include it, it would cancel out in the final step anyway, which is why it's not important. So by letting k equal to 0, we make our math simpler and neater to write. But in the end, what we notice is that mu is equal to e to the integral of whatever is in front of y, so positive, negative, whatever, p of t dt. And we get a general formulation of the integral in this form, just by using the definition of what we already know. So, in this case, always remember to standardize your equations, because note, our equation started off standardized. It had no coefficient other than 1. So dividing by t, I get mu is equal to e to the integral of p of t. Well, p of t is a positive 2 over t. The integral of 2 over t is 2 natural log absolute value of t, or natural log of t squared. Well, the e function and the natural log function are inverse functions. So these two functions cancel, leaving me with just t squared. Plugging it into the formulation, I get t squared times 4t dt plus c is all over t squared. Integral of 4t cubed is t to the fourth, so that simplifies the solution down to t squared plus c over t squared. If I happen to have a specific value that I want to travel on, where t is equal to 1, at t is equal to 1, y is equal to 2, I could choose a specific c value. Solve, plug in t is equal to 1, and solve for c. And you'd see I'd be traveling along this yellow arc here. Note that this technique, while technically giving you a result, might not give you an analytic result. It might not give you a result that you can actually do yourself. Notice in this case, I can't integrate e to the s squared over 4. It actually has its own special name. So instead I have to use something like a software system like Mathematica, Maple, MATLAB, or something else in order to approximate or actually achieve the true results of my solution. So this solution does exist, I just might not know or have a form to represent it. But that is the solution.